Bharani from Spider. Before starting this workshop, let me ask you a question. What do you guys think about interplanetary system? Any guesses? Anyone? We'll try to make this session as interactive as possible so that it will be easy for you guys to understand. Any guesses? It may be right or wrong, no worries. Just make a guess. Okay, we'll start this with a story, an interesting story. The story of Mars and Earth. Okay, as if we are in the year 28 and Elon Musk's Mars mission becomes very successful and he makes living possible on Mars. So what will happen? Due to overpopulation, obviously half of the population will be in Earth and half of the population will be in Mars. So, as if you are in Mars and you want to access a Wikipedia file because you forget how Wikipedia looks like. So you are searching for a particular Wikipedia page. Like, you know, right, the distance between Earth and Mars, it is so large. So it will take so much of time for the file to travel between Earth and Mars. So what will happen? It takes so much of time, almost 24 minutes. So assume you are sitting before your laptop for 24 minutes waiting for a single Wikipedia page. It won't be good, right? Obviously, everyone will start feeling irritated, right? So there should be a solution for it. Any guesses like how we can make that time go low, like we can access the file so quickly? Any guesses? Okay, now we are getting it very quickly, right? If we are in Earth and the file is also somewhere located in the Earth, so we are getting it. So if the same file is in Mars, we'll get it quickly, right? So that will be the solution to it. Before diving deep into what this interplanetary file system and stuff, we'll start with some basic prerequisites which will help you understand what IPFS is.
Before getting into this interplanetary stuff, let's actually get to know what exactly happens in Earth. Like what's exactly happening right now in our day-to-day life. So this is an image of Instagram or and this is Google. So you always be using Instagram everywhere, right? So what you do? Actually in Instagram we used to scroll through a lot of reels, a lot of videos. So something that is interesting is that those videos or reels that you see in Instagram are not exactly stored in our PC or in our computer. So, but still we are able to access it. So these are not stored in our mobile phone, but these images have to be stored somewhere in order for us to access it, right? So you guys have any idea on where these images are actually stored? So yeah, in cases, like where do you think these files are stored? Like these images or videos that you see? Yeah, got it. So these images or videos that you see will be stored in a server, inside the server. So what exactly is the server? So let's make it simple. Like we have a PC and we have a file stored in the PC. Yeah. So servers are nothing but they are just servers. They have powerful machines. Then we have a limited RAM, but servers have larger RAM or larger storage. They are capable of storing a lot of data and processing a lot of data. So this is basically a server. So let's take a simple example. So this is something that we could all try to do. Let's say we have the teachers or the jobs have given you some assignments, right? Yeah. So let's say I'm given an assignment. So what I usually do is I used to ask my friend for assignment and he used to send me an assignment and I used to do it. So this is what actually happens. So how about you guys? Are you the smart kids who do the assignment and see your friends or you do follow the same thing? anything as it. So this is what actually happens in server-based network. Let's say I want to find. So what I actually do, I approach the server. I say, server, I want to find. Just use this. So the server sends me the response that is find. The server sends the find to me. So this is something that happens in server-based network. So the example you saw, I was asking a friend. So I said I was calling my friend. So in order for me to do that, I should have a phone number. And even my friend who's there out there, who's going to send me the assignment, will also have a phone number. So just like that, in computer networks, we have IP addresses. As you can see, the numbers are here. These are all IP addresses that uniquely identifies a device and network. So if I want a particular piece of data for the server, I would use this IP address. Just like the phone numbers you have in the example. So simple, yeah. So you see, Google has this IP address. So if I want to access the data from Google, I'll be using this particular IP address and I'll be asking Google, send me this data, and Google will be sending it. So not just servers, even people, like RPCs, our mobile phones, everything is not IP address. So this is how actual computer networks work. But more often we don't use this IP addresses in the everyday life. Rather, in order to contact Google, we use google.com. In order to contact Instagram, we use Instagram.com and things like that. So how exactly that is handled? So let's say we have another server that's called the ENS server. Again, not too complicated. Server, again a server, all the machine out there. The job of the ENS server is that it translates those alphabets or Google.com, Instagram.com, this translates this to the IP address. So people are not going to put numbers. IP addresses are actually numbers. So these ENS servers help us to translate the text or alphabets such as Google.com, which people know. So in a second, let's say we have a person and say, get this file from this Google.com. So what will happen is the address will go to the DNS server. The DNS server will give it the IP address. So we will actually access the file from our server only if we have an IP address. So once you say, get this file from Google.com, that particular address will go to the DNS server. And the DNS server will give it the IP address of Google.com. Here it's like 1.2. So this is the IP address of Google. So it will be the IP address of Google and then that particular address will go to the Google server. So this is how the server-based networks work. So now let's see how exactly a peer-to-peer network works.
Okay, yeah. Before starting this idea, at least 3 to 4 of you to just volunteer to the stage so that I can explain it to the live demo. It will be very easy for you able to understand. Just again, 3 or 4. The thing can comment first. Just for instance, any of you is volunteer to go, just come, no worries. We are not going to have any question. It's not. Any of you volunteer? Okay, sir. Like now, before going to what peer-to-peer network, that is P2P network, you will first just explain what a server-based network is. Assume that it is a server. As we told before, server is just a powerful computer. This input so, assume he is the server. The server is like an abstract device basically. What would go setting like, see, if the assignment is given, probably who is going to complete the assignment, right? So like he will know all the answers, so he obviously completed. So he will have the answers. And then there are 2 people in the class, who wants to copy assignment on the number. So what they will do is they will go as the top of all the assignment. So assume that these people are the clients, that is the people who want the assignment from the server
So before we go to the undertakes, you should actually know what is hash. So any of you here in talk hash before, you have any knowledge of hash? Yeah. Yeah, it's kind of right.
Yeah, okay.
So actually, let's say I have a black box, and what I'm doing is I'm just putting file into the black box. So what will happen? If I put a data into the black box is going to give me a special code. Am I audible? So if I put a data into a black box is going to give me a special code out of it. So this is basically hashing. So the black box that I was speaking about is called a hash function, and that special code that I was speaking about is called the hashed text. So how hashing works is like, I said that's a black box, right? Let's say I put the same data into the black box, I will result into the same special code. The code for the same data will not change. For example, I have a text file which says apple. Okay. So I'm putting an apple into the black box. That is, I'm giving it to the hash function. I'm just giving it to the hash function. So it will give me a hash text, a special code over there. So the next time I put the same text file, the apple text file, it's going to give me the same hash text. So this particular text that I get for the same data will not change. Okay, this is one of the property of hash. So another property is that let's say I put a text file which has apple text file, the same text file, I get a hash, and now what I do is that's a 39 paragraph of text file. Okay, that's a 39 paragraph file. I'm putting that text file also into the black box, and that black box will give me a special code called the hash text. So the hash text which I get for the apple text as well as the 39 paragraph will be of the same length. Okay, so can get it. So be a huge data or a small data, for any data I'm going to get the hash text of the same length. So for the apple text, let's say it's like it has 10 letters in it. Let's say the hash text has 10 letters in it. Even for the 39 paragraph, I will get the hash text and again have 30 letters in it. So it will be of the fixed length. The hash text that we get for the different data will be of the same length. So okay, so here you can see like that's a data 000. It's a data. I'm feeding it into the hash function. I'm getting an output, the hash text. Now what I do is I just take a minor change. I just change this 0 to 1. So if you see the hash text of these two things are not same. They are not same in any ways. That's a big difference in the hash text. So this is again another important property of the hash function is that a small change in data will result in a large change in the hash text. So you can see I just changed this only one element in it, and the hash text I get is entirely different from the hash text that I get for this. So this is again another property of the hash function. So another important property is that another important property of this hashing is that it's a one-way hashing, which means I can just put the data into the black box and I can get the hash value. But if I put this hash value into the black box, I can't get the data. Okay, it's just the one-way matching, which means I can put a data into it, I can get a hash of this one. Let's say I put this particular hash text into the black box, I will not be able to get the data. I will be able to get the data, I will not be able to get the data. Okay. So it's just a one-way magic. I can put the data into it, I can get the hash text. So you can't retrieve a data back with the hash. So these are the properties of hashing. So why did we see it? So in IPFS, we use something called the content identifier. So a content identifier is like a fingerprint for a file. Like we humans have fingerprints, right? it uniquely identifies us and differentiates us from other people. So just like that, in IPFS, content identifier differentiates a file from other file. That is, if I upload a file, so yeah, so that is content identifiers. So where do we use this content identifiers is that we'll be using it in content-based addressing. So before like knowing content-based addressing, we'll actually know what is location-based addressing.
Yeah.
This actually encryption both of them. Okay, here is like you can get the data. Actually, this is what you can't get it.
You can retrieve the data back.
So, yeah. So let's see what is the location-based addressing. This is something we have already seen in the prerequisites. Like, let's say there is a server, just like google.com, there is a website called example.com, and it has a cat.png file in it. So I would like to access that cat.png file in that particular server. So what do? I just enter this URL in the browser, and what will happen? This particular example.com will have an IP address again. Okay. So the browser is going to request the server for the cat.png and it's going to give it. So what I'm actually doing is this cat.png is stored in one particular location. That is, this cat.png file is just stored in this particular server. So in location-based addressing, this is called location-based addressing. And here, what I actually know is, I know the location of the file. Right? I know what I actually know. I know like a cat.png file is stored in this particular location, in this particular IP address. So I'm very sure about the location. So that's why I'm retrieving the file with its location. Yeah, it says, yeah. So, but in case of IPFS, we'll not be using this content, location-based addressing. Why? Because in an IPFS network, if I upload a data into an IPFS network, so in IPFS network, you understood that there is no server or something like that. Anyone who's a part of IPFS are equal. There's no server or there's no special user in the IPFS network. So if I upload a file, let's say this is me and I'm uploading a file in the IPFS network, what will happen is this file will be split into many pieces, and one piece will be stored here, one piece will be stored here, or it will be like distributed across the entire network. So that way, if it is distributed, I'm not aware of the exact location. So let's say I want this cat.png file. I'm just uploading the cat.png file, and let's say the file is divided into many pieces, and it is given to like many clients. I mean, the cat.png file is with many peers in the network. So if I want to access the cat.png file again, I am not aware of the exact location of it. What I know is I want this cat.png, and I know that cat.png has a cat use. So this is what I know, and I'm not aware of its location. So that's where we'll be using the CAD concept that we saw earlier. So CAD is nothing but hashing again. So as I said, the cat.png file will have a unique fingerprint. I put this cat.png file in the black box that I spoke previously about with the hashing. I'll put it in the black box, and this black box will give me a hash value, which is called the content identifier, CAD of the file. So if I want to access the data in the IPFS network, what I will actually do is I will say that I will send a request to all the peers in the network saying I want this file with this CAD. So here I am not saying I want this particular file from this particular location. I am saying I want this particular file with this particular CAD. So what this client will do is they will check if they have this particular file, the particular file that I need, the CAD license, and if they have it, they used to like send it to me. So here we are not using the location, we are using the content of the file, the CAD of the file to access the file. So this is basically like content-based addressing, and that's how it's different from location-based addressing. So okay, let's see what problem exactly this content-based addressing actually solves. Let's say the previous example we saw process, then comes the hacker in between. Comes there, and I request the category key, the server also get the category. Let's say the category is coming from a desktop, but in between a server came, a hacker came, and he replaced this file with the log file, log image. Okay. So can I understand what I'm saying? I requested a category file from the server. The file is traveling from the desktop, and in between, in the midway, the server comes and hacker comes. It just replaces the cat image with the log image. So what am I getting? I'll be getting a log image. I went to the server and I asked for a cat.image file, but I actually got that log image back. So once I get the log image, I'll have to assume that this is the file that server actually is sending me. I can't verify it. I can't verify whether the file that I have received is what I requested for. So I guess if you see content based addressing, you will get it written actually. Let's say now I want a cat.py file stored in an IPFS directory. So as I said, this cat.py file will have a CAD, content identifier, which will identify that file in the network. So what I'm actually saying is like I'm saying an experience saying that I want a cat.py file and this has this content identifier. And also the same way, let's say that we have has the file and it says so the cat.py is running on the desktop, and again the hacker comes, he just replaces the cat image with the log image. Now even here the file that I will be receiving will be a log image. Okay. So what you can actually do is, again the black box comes. You're just taking the log image, you're putting it into the black box, and it will give you the CAD. So the cat.py file will have a different CAD. The log.py file will have a different CAD. Yeah, because the data is different. The cat image is different, log image is different, data is different, so the CAD is also changed. So I have the CAD of the cat.py file, but the file that I actually received is a log image which will have a different CAD. What I can actually do is I can compare the CADs of the file that I requested for and the file that I received. If both the CADs are equal, then I can say that that's no issues. This example you can see, if the CADs of both the files that you have requested for and that you have received, if both are equal, both are same, then it's fine. That's no hackers, no one like to do it. But let's say the file that I received will have a different CAD and the file that I requested has a different CAD. So what happened? It means that someone has included, someone has tampered the data that you actually requested for, right? So this is how you can actually verify the data that you requested for the same as the data that you received. So this way, the self-verification works in IPFS.
Now I guess I ordered the last. So now we know what content-based addressing is, what is hashing, what is peer-to-peer network, and distributed file system, everything you know. So now we can connect all the dots to understand the definition of IPFS evidence, right? So basically, assume these are all the nodes in IPFS, and assume like as I told an example before, he is the one who does all the assignments, so he will have the assignment. Now what happens is, this friend of him wants the assignment, so he will get it from him. One special thing about IPFS is, when he gives the assignment to him, he will have the copy and he will also have the copy. Basically, we can tell like maybe we will share WhatsApp, right? We'll take pictures of the particular file, like make a PDF of it and then share it. So he will anyway have the copy and he will also have the copy of the same file. Now this person may need it. So what he will do is he will see who is sitting next to him. So he will go ask this person or this person to give the file. So in this way, everyone will be able to access the file. So what happens now is, like everyone has the file. The specialty about this is, even if he loses that file, assume that this person wrote it but he lost it somehow. But he will be able to, like if he can find it out easily, because these two people will have the original copy of the file anyway. So this is how basically IPFS works. basically IPFS works. I hope you got it. Any doubts? What IPFS is? Got it? Or should I repeat again? You want me to repeat again? You understood this, right? This is like the basic concept of what IPFS is. Okay. Till now we saw what IPFS is, content-based addressing and everything. There should be a purpose for learning something, right? Obviously, there should be some purpose or some problem it will solve, so that we need to do something more. So, what are the problems that IPFS solves? Verifiability. As I told before, that verifiability is one of the very important key feature, because like it will prevent hacking. Basically, it will prevent the malicious actors to just come and edit the file, because it is a decentralized system and it is stored in everyone's file, everyone's local system. So no one will be able to just edit or delete the files. Decentralization. I explained this before. You know what decentralization now is. I did not explain it anymore. And data sovereignty. As I told before, the file is stored in different nodes all across the world. So what happens here is, if someone needs a file, he will see for the nearest node of him and he will be able to get data from the nearest node. In this way, it makes it easy for someone to just access the file.
So, in case of a centralized network or server-based network, let's say a file is stored in the network, I mean in the server, as we saw before, and I'm trying to access that particular data or file at the server, I'm able to get it fine. Let's say one fine day the server is down. Like, you are trying to access the file, but the server is down, so you wouldn't access it. So such centralized network where one point of failure, like in the server fails, maintain network distance. So such networks are not said to be resilient. So IPFS on the other hand is actually resilient, because let's say this particular node has the file and also this particular node has the file. Let's say one fine day this node just goes down, but what will happen? This particular node will also have the same file. So if any one of the people in the network wants the file, this node can actually serve it. So here, just one point of failure will not affect the entire network. The network will still be alive. So this is how IPFS is resilient. So IPFS actually improves the accessibility or the speed with which we can access the data, because since the data is many peers in the network, if I want a particular data, I could actually get it from my neighboring peer. So in case of server-based network, I will have to ask the server, which is at a long distance. But whereas in IPFS, the neighboring, the nearest client, nearest peer should be more nearer to you, and you can get the data easily. So that way, performance is increased in IPFS. So introductory is something we have already seen. So again, a server. So that's a server, and that's a file stored in the server. And let's say the file got deleted in the server. So if you try to access that particular file again in the server, you will not be able to get the file. You will get this not found error. The server will say that the file that you request for is not with me and I can't serve the file. So this is called introductory, which means the link that we saw, like the example.com/cat.png. Let's say the cat.png file got deleted from the server, and this link will no longer be useful. So the link would have gone out. So this is introductory. So how exactly IPFS eliminates introductory? Again, since the decentralized network, many peers in the network will have the same file, the copy of the same file. So even if a file gets deleted from one peer, the other peers in the network will have the same file with them. So they could actually serve the file. So this way, link problem is eliminated in IPFS.
Yeah. Now moving on to what are the disadvantages of IPFS? As everything will have its own advantage as well as disadvantage. The first disadvantage will be limited accessibility. As IPFS is developing currently, like unlike HTTP, it cannot be accessed on all the browsers. Basically, we can't access an IPFS file on Chrome. We can access it only on few browsers like Brave. You all know Brave, right? So we can access it only on few particular browsers, and this is how basically an HTTP request looks like. If you when you search something, this will be the request which will be sent to the node. So next disadvantage will be lack of permanence. We know it is getting stored in multiple devices, but though what happens is there is a thing called garbage collection which happens. What exactly does garbage collection do? It checks for the nodes, okay? Like it will check how much time the nodes is utilized in a particular period of time. Assume if the node is not utilized for a longer amount of time, we didn't use a particular node for a very long time, what happens is it automatically gets deleted. Basically this is how garbage collection works. So due to this, if the node gets deleted, we can't be able to access it. Like sometimes we need to access a particular node which we stored before, but that node doesn't exist, we can't access it, right? So this leads to lack of permanence, and it creates redundancy of it. Like all of you must have thought now itself, in every one of the devices it gets stored, right? So automatically it leads to increasing storage in all the local devices. So it obviously reduces the performance of the device that everyone can just see right now. So what happens now is they came up with a solution for this, which is called file point, which will be discussed in the next part of the presentation. Now everyone can turn on their laptop so that we go for the hands-on session. Just open the IPFS.
Once you open the IPFS desktop, this is the first page that you will land on. So let's see what exactly is included in these pages. So first thing that you could see is, it says hosting 6 MB of data. So what it exactly means is that, so once you have installed this IPFS desktop, all of us who have installed this in the computer will now be a part of IPFS network itself. So now you'll be able to upload files to the IPFS network as well as receive files from the IPFS network. So officially, once you have installed this, you are a part of IPFS network. So that being said, the first thing it says is hosting 6 MB of data. So what it actually means is, since I am a part of this PC is part of an IPFS network, there will be other peers in the network who will actually store files in my PC, right? So it says 6 MB of data is being hosted because there are other peers in the network who are storing files, and that file size is about 6 MB. So this is something that it says. The other thing it says is, I have discovered 14 peers. My PC is connected to other 14 peers in the network. So this is something it says. So we'll see something interesting in this. So the next tab that you go to is files. So what you could actually do in this is, you can actually upload a file to the IPFS network. So let's see how we actually do it. So you could see an import. There is on the top of it, there is an import, right? Import button over there. Not import. So that's the import button on the top right. So if I press this import button, I'm getting 4 options right here. So let's say I want to upload a file. I would like to upload a file to IPFS network. Let's say I'm uploading this file. So here, okay. So here what I have is, I have this 3 text files, okay, which says these text files are like hello 1 and hello 2. Wait, okay. One sec. So I'll try editing the content of this text files. Let's say in the hello text file, I'm just typing in hello, okay. So the same hello, I'm just closing this, and let's say in the hello one I have hello world, okay. Fine. So and in hello 2 again I have the same hello. Let's see what happens if we upload these files in the IPFS network. Okay, so we have 3 different text files. The first text file which says hello, second text file which says hello world, and the third text file again hello. So what I'll be doing is, I'll try to upload these files to the IPFS network. How do you do it? Just click on the import button over there and click on files. So you can upload any file, be it an image file, be it any file, you can upload it to the IPFS network. I'll just try it with the text file, okay. So I try uploading this hello text file. Okay, fine. So now that this file is uploaded, it says hello, and at the bottom you can see there is some long text. Can you guys guess what exactly is this? The text, the string that you see at the bottom. Yeah, exactly. So this is the CID of the file. So again, as I said, this is the content identifier, that is the hash value. So let's say I try to upload the other files also. So I'll try uploading hello1. So the content of the hello1 is hello world. So say now I'm uploading hello1, and hello1 has a different data ID. So preferably the CID of hello1 file should be different, right? So let's see, let's find out. So I'm uploading it, and as you can see, the CID is also different because the content of the file is different. So obviously the CID has to be different, and it's different here. So now I'll try uploading the hello2.txt file. So again, the content of hello2 as well as hello are same. They have hello text in them. So both of their content are same. So what will happen? Will the CID remain same or it will change? So obviously it has to be same because the content is same. So the CID has to be same. I'll try it. Yeah. So as you can see, the CID of this file and as well as the CID of this file are same because both of them have the same content in them. So I guess you are able to do it. Yeah. So you have seen the CIDs being different for different content and same for the same content. So let's see what other options we have here. So if we click on these three dots over here, you could actually get some amount of options over here. So the first one says share link. So what does it actually mean? Let's say I want to share this link. Okay, it gives me a link over here. What you could actually do is I can share it with my friend. So what will happen if I share this? My friend will go to this URL and he'll be able to get the file as long as I'm online because that's my service here. I'm serving the file. So if you look into this URL, you will find the same CID here, right? So the CID of the file is here. So that way, even if you share this file to your friend or someone, your friend will be able to access this file. So let's try pasting it. So yeah, if I paste this file the browser, I am able to get, so it says hello, the content of the file. So I got it, right? So this way you could share this link to your friends or someone, anyone in the network, and you could actually enable them to access the file. So other options. So here you could see copy ID, obviously copy the CID. So let's say I copy the CID, and let's say you want to access a file in the IPFS desktop itself. So at the top you will see a text box, right? If I paste the CID here in this text box, and if I say browse, yeah, again I will be able to access the file. So you could enter the CID in the text box and you could get the file. So if you have the CIDs of any other file, you could actually enter there. I just copy the CID, I will paste there, and if I click browse, it's going to give me the file again. So you can browse files in the IPFS desktop. So what are the options? Yeah, inspect. So inspect just gives the basic data of the file, its size and CID and the type, like it's a file, and this is something that is too complicated. So it gives the basic data. Fine. So that's another option called set picking. So what it actually does is, you have seen about garbage collectors, right? So what a garbage collector will actually do is, let's say a file is stored in multiple locations. Like let's say I upload this hello file. Okay. So once I upload this hello file, let's say it gets distributed across many peers. Like that is a peer there who has this text file, hello file with them. So we are just doing it for demo, right? So we will not access this hello file anytime in the future. So the peer which is storing this file has no use because no one is going to access this file, and the file hello text file will be of no use in the later period. So there can be many files like that. Let's say someone uploads a file and just forgets, or the file is there but it is never accessed. So in that case, the storage is going for waste. So what a garbage collector comes and what it actually does is, it just scans through all the files and it will actually delete those files which are not accessed frequently. So let's say I put this file and I don't access for months together. So what will the garbage collector actually do is, it will scan through the files and it will actually find this file which has been accessed a month or a year or something like that. So what it will do is delete the file because this file is not frequently accessed, and storing this file in the IPFS network is of no use because no other peer in the network actually is requesting for this file. So that way unused files in the network will be deleted by the garbage collector. So yeah. So set pinning, what it will actually do is, it will instruct the garbage collector saying that even if this file is not accessed for a long time, or even if no one uses this file, just store this file permanently. So this is what set pinning will actually do. If I say I'm setting this, and if I click on apply, you could see a status here, and you could see I was just setting the pinning in this hello file, but this hello2 also got it because the CIDs are same. So because those two files have the same CID, they will not be deleted in the future. Like even if this file is not accessed for months together, this file will not be deleted by the garbage collector and it's going to remain. Okay. So again, download is just downloading the file, and again rename, just if you want to rename. Okay, so that's the option which says remove. What I can actually do is I can remove the file, but I just have one more filters. Let's say I'm removing this file. I just upload this in the IPFS network, and let's say there's another peer in the network who has the copy of the file. Okay, they have the copy of the hello text file with them also. So if I actually remove it, I'm actually removing it from my PC. Okay. So if I remove this file from my PC, it actually remove the file from the entire IPFS network? No, it won't, right? Because a copy of the file is already there in another peer. So that way, if you are uploading files to IPFS, you are given an option to delete it just from your PC. So if you click on remove, that doesn't mean that this file will be deleted from the entire IPFS network. Other peers, if they have a copy of this file, it will still be available in the IPFS network. You just delete it from my particular PC. So the other option says publish to IPNS. So what is IPNS? You will learn it in the upcoming presentation. So I'll go to this. This is all about the files tab there. If I go to the peers, I can see I'm connected to about 1 or 2 peers. So you could see the peer details here. Something that's important is that, so here you see a peer ID, right? So what is a peer ID is that, so each and every peer in the network will be uniquely identified by this peer ID. So each and every client will have a unique peer ID with them. So let's say I have this peer ID, you will have a different peer ID, and anyone in the network will have different peer IDs. That will be used to uniquely identify a peer in the IPFS network. So here I could see there are like many peers that I am connected to. So in an IPFS network, there would be like thousands of peers, but I am just connected to like around 465 peers from my PC. So I'm not connected to all the peers. I'm not connected to all the 1000 peers. So how is this actually happening? You will be seeing it in the next presentation. Yeah. So this is all about IPFS desktop. So if you guys find time, just go and play with this IPFS desktop. It will be really interesting, and try sharing this. I said right. You could share this link with your friend and try if you could actually access this file. So you will be able to access this file as long as you are online, because you are the one who are serving the file. That's no servers or nothing in the IPFS network. So as long as you are online, your friend will be able to access this file. So try sharing it with a friend and enjoy.
Learned what IPFS is, what content identifier is, the advantages and disadvantages of IPFS. So now we'll see how files are accessed when a CID is given. So when you upload a file to IPFS network, the file is divided into smaller chunks called blocks, and redundant copies of these blocks are distributed across various nodes that participate in the IPFS network. So when a node requires a set of files, it sends a list containing the CIDs that refer to these files. So this list is called want list. So let us understand the mechanism with the help of this simple network. So here there are 4 nodes in our simple IPFS network: A, B, C and D. A is the node that requires a file. So it sends the corresponding CID, the want list with the CID to all the other nodes that are directly connected to A. So the nodes that are directly connected to A are called peers. B, C and D, they are arranged in the increasing order of their distances from A. So all of them receive the want list and they respond to the want list with a message saying whether they have the CID or not. Since C and D are farther apart from A than B, their responses are different, as you can see. A simply ignores the responses of C and D because it has already received the response from B. Now, to the message sent by B, A requests B to send a file corresponding to that CID. So to which D replies with the file. So this mechanism is not as simple as it sounds. We'll see more about this in the later part of the session. But there must be a way to identify which peer has which CID. So that's where distributed hash tables come in. So distributed hash tables, they store peer ID, CID pairs. So peer ID is a unique identifier assigned to every peer participating in the IPFS network. It does what CID does to the content. It uniquely identifies the peers. So this table basically maps peer ID to CID. So whenever there is a want list, the nodes that are participating in the network can refer the distributed hash table to check whether they have the CID or not. If they have, they can send the file to the node that wants it. If it doesn't, it goes on to the further steps. So if it doesn't, it forwards the want list to the peers that it is connected to. So there can be many peers participating in an IPFS network, like there can be billions of peers, but every node can be connected to a limited number of peers. So how are these peers chosen? There is a radius factor associated with the IPFS network. So all the nodes that fall within the radius are grouped into a bucket. Here as you can see, B is the node that's going to send the want list and DC is the radius. So all the nodes that are within the distance DC from B, they are grouped into one bucket that is specific to B. So here A, C, D and F are grouped into one bucket. A, C, D, E, D, they are grouped into another bucket and H is in a separate bucket. So let's say A wants a file. It sends the want list to all peers that it is connected to. That is the nodes inside the bucket. So the want list reaches A, C and F. If any of these peers have the file, they send it back to B. But if they don't, they forward it to their peers. Let's say A does not have the file. So A forwards the want list to the peers that it is connected to, that is E, E and C. So this process goes on iteratively until the required file is received. So in this way, multiple peers, even if the peers are not directly connected to the node, they can be traversed, they can be queried for the file. Okay, so now we'll move on to interplanetary name system. CIDs are hashes, so they contain digits and numbers put together, and we human beings cannot remember CID. So interplanetary IPNS, it simply assigns a human readable name to the CID, so they can be easily remembered and referred to. Now that's not the only advantage of using IPNS. It also provides mutability of provides a feature of mutable content. So let's see what it is. So content in the web, they are subjected to change. So let's say there's a file in the IPFS network, and the files are obviously hashed using their content. So if the content is changed, the CID that refers to this file will also change. So multiple versions of the same file will have different CIDs. A user might find it difficult to locate the most recent version of the file, right? So that's where IPNS steps in. As I said earlier, it assigns a unique name to every CID. So when the content is changed, the CID obviously changes, but it replaces the old CID. So the new CID is simply updated in the IPNS record. So the same IPNS name will point to the new CID. So, although the CID changes, the IPNS name remains constant. So the users can still use the same IPNS name to refer to the most recent version of the file. So that's mutability of content, and it also provides DNS linking. So you guys know what DNS is, right? In the traditional HTTP based network, every IP address is assigned a unique DNS for ease of referring the web page. So similarly, a domain name can be assigned to IPNS name or CID. So users, this provides connectivity between the traditional HTTP network, the centralized one, and the peer-to-peer IPFS network. So users who are not part of the IPFS network can simply use the domain name. They can type the domain name on their browsers, and the corresponding file that is in the IPFS network will be returned. So this feature is being used by some browsers like Brave and Opera, provide access to the IPFS network. So now we are at the backbone of IPFS network, IPLD, that is Interplanetary Linked Data. So multiple various nodes participate in the IPFS network, but there should be a uniform way to represent and store data so that it can be easily accessed and it can be easily retrieved. That's what IPLD does. It enforces a uniform data structure across all the nodes that participate in the IPFS network. So the data structure that is most commonly used is DAG, Directed Acyclic Graph. So you guys might know what a graph is, right? So a graph consists of many points or nodes, and these nodes are connected by edges. DAG is directed, which means there is a direction associated with every edge. A points to C, A points to B, but C cannot point back to A. And it is also acyclic. You cannot find a loop or a cycle in this graph. So So as said earlier, hashing is a one-way operation. When you give content, you get the hash value, the CID. But there is no way to retrieve the content from the hash value. So how exactly IPFS network retrieves the file when you supply the CID? So that's what DAG accomplishes. So as I said earlier, every file that is uploaded to the IPFS network is broken down into chunks called blocks. So let's say these orange rectangles represent those blocks, and each block is associated with a CID. Now, two or more blocks can be combined to produce a new block. So this block will refer to the CIDs of the blocks that are combined. So as you can see, like two blocks are combined to produce new blocks, and the CID of this block refers to the ones that are below. So these two blocks are called the child of this block, and all the data chunks or the blocks that the file is divided into are called as leaves because they don't store reference to any other block below them. So these are leaves. Again, this subsequently, the next level of blocks can again be combined to produce newer nodes. So all of these nodes converge to a single root. So each of these blocks, they have a specific CID. So the CID of the root can refer. The CID of the root is enough to access all these data chunks. So it is the CID of the root that is sent in the want list. So yeah, so that CID can be used to refer all of these data chunks, and these data chunks can be combined, integrated to get the file, and that file it will be sent to the one who is requesting it. Yeah. So uses of IPLD is basically to enforce a common data structure, and it also offers many data types like string, integer, float, boolean, etc. And these data types can be combined to produce custom data structures. Yeah. Now over to Naveen.
Yeah, so far we have seen quite a lot about IPFS, right? Now we're gonna move on to like things that are slightly different from IPFS, but still like it is still a decentralized sort of thing. But we're gonna move away from IPFS for a bit. So before moving away, I just want to touch on one point of IPLD is that IPLD basically enables the fact that you can join two different kind of things together. So what IPLD basically helps is that suppose because it enforces a same data representation from everything, it kind of links different things together. So one of the examples is that it can link let's say Git, and it can link Bitcoin. So like certain transactions in Bitcoin would be able to link to some versions of Git. Similarly, there can be different ways of in which this can be done. And another example is how Ethereum can be linked to IPFS. So IPLD is basically like that common structure which enables such linking because it enables like a sort of uniform layer between all of them. Now, so basically before we'll be moving on to one specific example where like cryptocurrency is linked with IPFS, and that is called Filecoin. So this is also mentioned before by Bharani, where like we have mentioned that in IPFS there was a disadvantage that like it's like you don't have incentives to do things, right? Because there's there's no benefit of storing something. Yeah, so that's where Filecoin comes in. But before moving towards that, we'll be diving a bit more into cryptocurrency and blockchain. So yes, introduction to blockchain. Now, I guess most of you would have heard about blockchain because it was this huge buzz like last few years with blockchain, Web3, NFTs coming together. Now, do you guys know what is the basic like underlying things of blockchain? Well, like the name implies, it's basically just blocks which are linked together using hashes. So now, like I'll give you a high-level overview of what happens. Essentially, different blocks are there, and each block has the value of the previous hash. So basically, like every block, suppose if you have like 10 blocks here, right? Each of them is linked to the like, right previous block. So, and basically, like every transaction that happens are stored in these blocks. Now, how is blockchain different from, let's say, like a regular, let's say, you pay someone else, right? So, for example, if you are paying someone else, only both of you know that is happening, yeah? While in blockchain, it's like very different. It's mostly decentralized, like we have heard before. And essentially what happens is, whenever, let's say, you want to make a transaction to someone else, right? So, you're essentially going to advertise to everyone that you're making this transaction. So, basically, your like, block is created saying that this transaction is happening, and like from one specific address to the next address, like this certain transaction is being held. Now, this block is sent to everyone else. So, for example, if you are sending to right? Now this block of transaction is given to every other person in the, like everyone in the blockchain network. And what basically it does is, so specific to every kind of blockchain, so like there's Bitcoin, there's Ethereum, each of this has a different method of finding a certain value inside the blockchain block. So the blockchain doesn't just contain like the transaction and like who to who. It also contains a special value called nonce. We won't be dealing too much into it, but essentially like it takes a bit of time to calculate that nonce, and it's specific to different programs. So like Bitcoin would have a different way of calculating nonce. Ethereum would have something else. So essentially, once this block is shared to everyone else, like everyone would like whoever is interested would try to find the value of nonce such that a certain condition is met. Yeah. And so once this condition is met, this is like basically stored back into the block, and the whole value is hashed. Now this hash would contain everything, like the nonce as well as like from whom to whom and the value. So these are all values plus certain others corresponding to the different type of blockchain. But in general, these are the things which would happen, and the entire thing is hashed. So now suppose, so the benefit of blockchain is that because everything is linked together using a hash, like everything has a specific hash. So this would contain the hash of this would contain the hash of this. Suppose if you want to change like a certain transaction here, it will be like instead of going from her to here, it will be from her to him, for example. If you change that, because the hash value is calculated from the entire list of items, the hash will change. So, like this block wouldn't be linked to that like this block anymore because the hash is. That's why it kind of enforces the safety that like things are safe, as well as the fact that even if like you change something, right? Because everyone like you're sharing this information to everyone, and every single person would have this entire ledger with them. So because of this, even if like there is changes in one person's device, it would sort of, because everyone else has a different thing and it is like a different thing, you would essentially correct it back to the original. So that's why blockchain is like kind of like it sort of brought a different shift into how transactions are held. And because there's a lot of anonymity and stuff in the sense that it's only like you're telling addresses, there's like issues with blockchain as well. That's why we didn't completely shift over. But yeah, in a high level overview, this is what blockchain is. Now, with this knowledge, we go to Filecoin. So Filecoin is complete, like it's kind of similar to IPFS in a way, but it's not exactly like how IPFS works. So in IPFS, we're essentially having like these files, right? It's basically shared to everyone. Yeah. So there's no and the thing is, when you're saving the files in your server or something that you're having, you don't have any incentive to actually save it. Yeah. So there's no benefit to the person who is like storing the files to actually store the files in an item. So that's where file comes in. It's somewhat similar to IPFS in the sense that there is a person who is storing the files, but the difference is that there is an incentive. So basically, the person who is like telling the person to store the file, right? The client who is requesting it would pay a certain file coin to the person, and they would basically from this they can store the files in the memory. And how it is linked to like Filecoin is also a cryptocurrency, and basically it's similar to how I said before. There's the entire ledger which is shared to everyone. So there's a sort of enforced thing. And like similar to how I've said before, there's like I've mentioned that people try to find the correct thing. Yeah. So in a similar way, when in Filecoin, when someone tries to find the correct thing and saves the file, right? So the Filecoin also sends a reward back to the person, and that's also the incentive of trying to store the file. So yeah, that's mainly it about Filecoin, and so we would be moving on to something quite different, which is version control system. Now, as I said before, it's kind of completely different from IPFS and Filecoin, but the common thing that links between everything is the sense that it's like a way of storing files, but as well as it's basically linked together with hashes. So we'll be moving a bit more into detail of what version control system is. So do you guys know what's version control system? Have you heard about it? Do you know why we do it? Yeah, so exactly. That's mainly the reason that version control system is there. So basically, to reiterate, it's basically like a way to kind of store changes in files. So the thing is, before the version control system existed, yeah. Suppose if you had a code base, yeah. Now you wanted to make a change, but you don't know if the change that you make would break everything up. So for that, what you could do is you could just copy all the files again to another folder, work on the entire thing and see if it breaks. But the problem with this is it's kind of going to create a lot of redundancy, right? Because you're going to copy the files prior to things. There'll be a lot of difficulties as well as the fact that when multiple people come together, it's difficult to do this entire thing. So that's where version control system comes in. It's essentially a way of controlling the versions of your code. So essentially your code would have different versions which is stored in GitHub, and you would essentially have different ways of interacting with it. So basically, that's the use of a version control system. We'll move on to how it works in a bit. But yeah, basically it helps a way of making changes to the file without breaking everything, as well as it helps multiple developers work together. So yeah, these are the basic concepts of Git. So essentially, when we say Git, right, we have a central repository where all the files are found. Now, suppose if you wanted to make some changes, so essentially, without working on the same branch, without working on the same thing, you can essentially create a branch and start making changes to that. Now, the benefit of doing this is that suppose if it's basically a way so that you can test out a feature. So multiple people can start branches from a certain point and they can try testing out features, and if it works, they can merge it back. So these are the main points, which is merge and branch in version control they are like the snapshot of all the changes that are made. So, and the interesting thing is that for version control system like it, all the changes that you make, it doesn't store the entire like file again into the thing. It'll just tell like these are the lines which are changed and these are what it will change. So essentially it's just storing that information as commits. So because of this, like it helps in the sense that like suppose if you reach here, you find that this commit is broken, you can easily roll back to the previous commit, and that's essentially the benefit of that. Yeah. I mean, so in this slide, it's just basically like in a kit, right? So one main thing is that once you download a repository, for example, you're going to have like all the previous commits in the .git file. So because of this, like what you can do is like suppose if you want to change a different branch, right? You're essentially pulling like all the commits from that branch to your working directory. And if you want to like commit to the branch, essentially you are adding a commit to that like list of all the commits. Yeah. So these commits are linked together by hashes. Essentially, each commit is also their hash, and they are linked to the previous hash. So in this manner, like basically it's kind of hashes like a linked structure, similar to how blockchain works. Like in yeah. Staging area is basically like a certain middle ground so that you don't have to commit all the files, but you can keep it in a certain area where like you don't, like suppose if you make a lot of changes, right, you don't need to commit everything. Essentially that's why we have a different area called staging area, where suppose if you make 4 files, like changes in 4 files, you can just stage like one of the file and commit just that, or stage 2 of the files and commit just that. Yeah. I mean, okay, so we'll be like just brushing over this, but essentially every commit, like every commit also has an inherent hash file. So essentially, like similar to blockchain, it is also linked to the previous hash. And that's how it basically works, in the sense that every commit that you do has a certain hash based on it. So because of the certain hash, like similar to blockchain, you can't just like change things in the middle and like affect everything else. But you can like have branches and changes. And I mean, yeah, this is mostly about it, about version control system. So the main reason that we actually went to version control system was that we at Spider, right, we tried like thinking of how we can use IPFS, and we realized that we can like version control system in essence is similar to how an IPFS works, because there is like these hashes which are linked together, and there's a way in which we can link actually how like version control system works as in sort of model it using IPFS. And that's basically what we did. Like we made a program called Statik which does exactly that. It's kind of similar to how version control Git works, but we use IPFS for doing that. So we'll be showing a demo of Statik right now. Yeah, essentially now I'll just go to an empty directory. So essentially what I would do is, yeah, I went to a completely empty directory, right? Now I'm going to take my IPFS, okay, so essentially for doing the thing, we are linking it to our IPFS account. Yeah, we're going to just copy our API, which is essentially like a link to our IPFS desktop application, yeah? And we're going to use this to be IPFS. So static init using the IP, basically the link to my IPFS. And this would create a static, one sec. Yeah, I'll just create an empty repo. So you can see there's nothing inside the repository, yeah? There's only the previous things. Now I'm going to create, I'm going to basically initialize static. So if you just remove the thing, I'm going to So static is basically like the IPFS control system that we are using, and it's basically helps us to create a sort of repository which is similar to how a version control system of Git works. Yeah. So we're going to initialize it using the using the IP like the API that we found from our IPFS, and so we created the static repository in this this thing. So now if we check our LSA files, so these are all the hidden files, and we can see that static is a repository which is inside our folder now. Now suppose like similar to how version control system works, we are inside we're inside main branch right now. Okay, so suppose if I create a like a.text, yeah, suppose cat.text, and then I'm just gonna write cat, I'm saving and exiting. So now there's cat.text inside the main branch. Yeah, now the thing is here we can go to now this is only within the branch. Now the thing is, this is like inside the branch, but it's not saved into the like the repository. So what you could do is, it's similar to Git. So if you guys know like the commands of Git, it's kind of we model static in a way that it's similar to Git, but the other uses IPFS for like how it works internally. So yeah, Git static add cat.text, and then it adds the text into a staging area. So like if you remember the PPT before, we had 3 different sections. One was like a working directory where it was there before. We just added it to the staging area, and then now we're gonna commit it to the thing. So one thing is, I'm just going to cd.static. Okay. Yeah. So we're just gonna static add. Wait, are you guys comfortable with this, or should I just move to VS Code? I mean, you guys can understand this, right? Yeah. So I'm just using the CLI for everything, but it's the same thing with like VS Code as well. So here I'm just going to commit this as a certain thing. So let's just say cats. Okay, my bad. Yeah, cats. So here we committed whatever we have done, and we got the hash of that commit. So essentially now in our .static file, this hash is like basically stored under branch. Yeah. Now suppose if I go, so I'm just going to take LSA. So we can see this cat.text and .static folder. Yeah. Now what I'm going to do is, I'm going to go to a different branch. So I'll say jump, and I'll go to a different branch called test. So I move to a different branch test. So if I just go static branch, you can see that there are 2 branches and we are in test. Yeah. So in this case, what I'm going to do is, I'm going to create a different file. So for example, static, I'm just going to nano like dogs.txt. Yeah, and then I'm going to save this. So you can see that there's this file which is saved. Yeah. So if you look at my LSA, so there's cat, there's dogs, and there's .static file. Yeah. Now I'm just gonna remove everything. Now suppose if right now this is there in branch, but it's not committed yet. Yeah. So now if I want to jump back to main, I would be able to jump back because it is not like basic. It's not, we are not making any changes. It's like something which is completely brand new. So we would be able to jump back to main. But okay, we'll just get onto this point like later on. But if we go back to test, for example, now we're going to commit this. Yeah. So static add dogs.text, static commit as dogs. So we got this hash which is committed to the branch test. Yeah. Now suppose if I'm going to take, I'm just going to show LSA. So you can find all the files that are linked to this is cat.txt, dogs.txt and .static. Now if we move back to jump main. So we move back to main, and the special thing is it moved the commit back to a different commit. Now if we check our LSA, you can see that only cat.txt is there. So yeah, I mean this is like basically what a version control system in like Git also works, but we basically tried simulating that using IPFS, using static. So yeah, one different change is like suppose static, you can see that cats.text is cat, yeah. So I'm just going to change this to some other value. So we're just going to change it to, let's say, like birds, yeah. So I'm just going to save it and close. So you can see that in cat.text it's birds in this particular branch. Now if we move back, let's say static branch test, right? Static jump test. Yeah, we moved back to, okay, that's one difference, is that right now if you look at branch main and branch test, right? So branch test would have cat.txt and dog.txt, yeah, and branch main will also have cat.txt. So now the thing is, right now I've changed cat.txt, but I haven't like committed it yet, yeah. So I can't really move back to test because it has like for the cat.txt the main commit is the commit is like it's not completely changed, and we can't move back to test because like there is a file change but it's not committed yet. So that's basically that's error here. So I'm just going to static so yeah, I've done this. So now we are in main, yeah, static branch. We are in main. So now we look at the value of cat.txt. What is inside cat.txt? It's birds. But if we move back to static jump test, now we are moving the head commit to a different value. But so if we check LSR, so in this cat.txt is still there, but dogs is like a different commit that we did. So if we do if we show what's value inside, it will be cat. So we can see that if you guys know what's version control system, it's basically like the main functionalities of this. So essentially, like you can have different features in different branches. So if I just take chalk and explain, right? Suppose if I had an initial commit in main, yeah. Now basically we are essentially branching into two different things. We went to test it this time. Yeah. This is like when, suppose if there are two files, this had cat, yeah, cat, and then we basically moved on to this where we created like one file which has cat and one file which has dog, yeah, and then essentially we can also go back to this. After that we went back to main and then we change the value in this file to be words. Yeah. Now the thing is, this is also named cat.text, and this is also cat.text. So we couldn't move back because they had like different values. So basically we committed and we went back. Yeah. So I mean that's mostly it. So in VS Code I can show you. Yeah. So we basically used IPFS to create yeah, you guys can see, right? So basically we used Statik. We created Statik using IPFS, and essentially it's a version control system which would store like all the different things. Now here there is main and there is test. This is basically the hash of the head of those files, and we only need to know the hash of the head because like essentially, yeah, I mean it's like a linked list. So once you know this, you know everything previous, and you can like basically roll back, etc. So you guys know Git, it's something similar, and this is Statik is like what we did to replicate it using IPFS. That's why we link to the IPFS. Yeah, I mean, so that's the end of the workshop right now. So yeah, do you guys have any doubts or anything?